So 40 and last, a bacteria culture contains 1,200 bacteria and doubles every day. How many hours will it take the culture to reach 10,000 bacteria? Okay, because they told me it doubles every day, there is a little trick here. It says how many hours. So I'm going to put population at time t. I'm waiting for the little spinning circle. So population at time t is going to be 1,200 times 2 to the power of, so it told me it doubles every day, and I want my time to be in hours. So that this exponent is going to be days, I'm going to divide the hours by 24. And then I want to know, when does that get to 10,000? So the only unknown I have here is t. So I'm going to divide both sides by 1,200. So that cancels to 1. And I can cancel 2 zeros here. So 2 to the power of t over 24 equals, if I divide 100 by 4, that's 25. If I divide 12 by 4, that's 3. So I want to get at t. So I'm going to take log base 2 of both sides. So this undoes the exponential. So t over 24 equals log base 2 of 25 thirds. So 25 thirds. And then all I have to do to get t by itself is multiply both sides by 24. And this is going to be a little bit over 72 hours, because if I did 24 divided by 3, that would be 8, and log base 2 of 8, because 8 is 2 cubed, so that'd be 3 times 24, which is 72, so about 73 hours. But the answer they're looking for is t equals 24 times log base 2 of 25 thirds. And we'll go check their answer. So 24 log base 2 of 25 thirds. And they have a much bigger explanation than what mine is. And you can stop now, but here's the traditional way to work this problem. So if I get rid of all of this stuff, the traditional way is to use the exponential growth formula with base e. So that would be 1,200 times e to the, we'll call it kt because that's what they used. So k times t. Now we don't know what k is and we don't know what t is, but we do know that we double in 24 hours. So if I say 1,200 e to the 24k equals 2,400. So if we divide both sides by 1,200, we get e to the 24k equals 2. To undo the exponential, we're going to take natural log of both sides. So 24k equals the natural log of 2. So k equals the natural log of 2 divided by 24. Then we can go back and say population at time t is 1,200 times e to the kt. So I'm going to do that in the calculator. So I'm going to start a new problem with a graph, then 1,200. Actually, I need to go do the calculator. So I'm going to do fraction natural log of 2 divided by 24. Then I'm going to store that in k. So now I've got that stored. I'm going to go back to the graph. 1,200 e to the power of k. And then my variable here is not t, it's x, so k times x. And I hit enter, don't see anything because I need to change my window. So menu for 1, I'm going to go negative 10 hours to say 100 hours by 10, and say negative 20 to, actually let's go negative 1,000 to 15,000 by thousands. And there I have a nice graph. And then I'd go back in and say 10,000. And now I can go find the intersection there, menu 6 for lower bound, upper bound, so 72.4. And if we go to a calculator page, menu, algebra 1, so we want f1 of x to equal 10,000, but we already defined f2 as a constant function, 10,000 comma x. And if we do natural log of something divided by natural log of 2, that's basically log base 2. And if we get the decimal for this, 73, so about 73 hours. And that concludes this video.